Hello, everybody. Thank you very much for attending this session. In this session, we'll go over the tour of the heart of a mobile core network and the effort which VMware and Nokia are doing together to bring 5G and NEG core into the market. I am Ninad Desai, Senior Director of Product Management. I'm a service focusing on the service provider and edge business unit here at VMware. And with me is Sanjay Wadhwa. Sanjay, how about you introduce yourself?
Thanks, Ninad. My name is Sanjay Wadhwa. I head the product management for Nokia's mobile packet core, and I'm based in Mountain View, California. I'm delighted today to team up with Ninad. Together, we will walk you through key architectural and design tenets of Nokia's mobile packet core, especially the high-performance user plane function, as well as the VMware's underlying telco cloud platform in bringing best-of-breed solution to our carrier customers. We will also present a snapshot of performance benchmarking of Nokia's mobile UPF on VMware's telco cloud platform. Over to you, Ninad.
Thank you very much. For the agenda today, we'll start off with the 5G trends and the trajectory. We'll look at how Nokia has architected its NEG core solution. We will then go into the VMware's telco cloud platform and the details of this telco cloud platform. And finally, we'll end with the performance results, which we have done together. We have a joint lab between Nokia and VMware, where we have tested out Nokia's UPF along with VMware's telco cloud platform, and we can showcase the performance which you've seen through this testing. Sanjay, off to you to talk about the 5G trends.
Sure, thanks, Ninad. So yeah, let's look at some of the market trends and data points related to 5G. So for proactive service providers, 5G represents a huge opportunity, huge business opportunity. And this is very clearly borne out by acceleration of 5G build-outs that we see by carriers across the globe. So today, while consumer mobile broadband is the initial opportunity with 5G that is contributing to the initial growth in mobile data, various forecasts show fixed wireless access, 5G-enabled gaming, and enhanced and immersive media are expected to drive a many-fold increase in mobile data over time. And 5G is already starting to enable several emerging opportunities such as live sports streaming, enhanced video, 4K, 8K, 360-degree video, music and gaming, AR and VR, as well as consumer IoT services. So we are starting to see these emerging applications show up. And a lot of this is supported by increasing availability of the 5G-enabled smartphones that are hitting the market. Today, by and large, we have lower cost options with sub-6 gigahertz phones becoming available. But we also see share of phones with millimeter wave support that would allow much higher bandwidth will increase aggressively over the next 3 years. So that is one enabler for 5G services and applications to be used by the consumers. We also see as that 50% of the world today does not have a reliable broadband. There are various government initiatives we see, for instance, CAF2 in US, offered by the government for ubiquitous broadband, including rural. So all this presents a really good opportunity for both fixed and mobile operators to basically monetize this opportunity with 5G. And the percentage of 5G revenue for fixed wireless access is on the rise. I mean, there are projections where by 2023, more than a quarter of the total revenue from fast wireless access would be attributable to 5G. And just, over the next 5 years, the fixed wireless access connections will triple than what we see today. And almost a quarter of the total mobile network data traffic would be attributable to fixed wireless access service based on 5G. Ninad, can we move the slide? So then how does 5G enable these new services? So 5G as an access technology promises data rate of at least 10 times faster when compared to LTE speeds of today. This means that not only will the cellular technology with 5G improve the performance of use cases today, but it can power brand new and emerging applications, as we just discussed in the previous slide. Now, 5G access also will improve average speeds, not just peak rates. And because of that, more services are becoming possible, and carriers will be able to make use of the new frequencies that were previously unused for mobile, opening up all this new capacity. And then beyond, faster speeds, 5G is a key enabler for lower latency. And 5G will reduce latency to below 1 milliseconds. So, at beginning of 2020, there was a study done where latency was observed across 40 major cities with 4G, and it hovered somewhere between, 40 to 60 milliseconds, which is still long enough to be perceptible when you're using, let's say, augmented reality or virtual reality. So this reduction in latency is expected to make AR and VR ubiquitous. So the real driver of 5G is not just a single set of applications, but a broad group that is typically clustered around one of the three centers of gravity we show here, and can be categorized into enhanced broadband, massive machine type communication, and then ultra reliable low latency communications. And with the access supporting all this, it counts for nothing if you can't realize the full promise of 5G, with the core also needing to provide high bandwidth and low latency for these demanding services. And that is why dynamic network slicing plays a key role in providing SLAs and user experience with these services. So core needs to play the part as well with dynamic slicing, which can assure your SLA and user experience. Along with it, the core needs to be agile and automated, so you can have quick turn up for these services and do automated lifecycle management of these service slices. So a fully cloud native core with automation and performance optimized user plane, which we will talk into much more detail, are prerequisites to derive the full benefits of 5G. Ninad, can we move the slide? So then how do we see this evolution to 5G? So service providers' best bet is to evolve their network with a solution that allows them to run all different access generations in a common cloud-native software platform. So essentially converging NEG core, including 2G, 3G, 4G, 5G, and even non-3GPP access such as Wi-Fi onto one unified platform. And this would then greatly simplify the overall network architecture and will reduce CapEx and OpEx. With the NEG solution, service providers will have more control. They can migrate to 5G in their own time and in alignment with their own business needs. So it's really key that your single core is NEG. And as we all realize, 5G initially is not going to be ubiquitous. So combined 4G and 5G control and user plane will provide seamless service continuity via 4G, 5G interworking. So basically 4G and 5G will coexist, and the core needs to provide interworking between 4G and 5G for service continuity and the experience that subscribers need. So keeping that in mind, Nokia has executed on this NEG core, where a single instance of a network function in the core with a consistent implementation provides support for 2G, 3G, 4G, and 5G, and even non-3GPP access. So this is really, really key and something to keep in mind. Can we move the slide, Vinod? So let's dig a little bit more on Nokia Packet Core, which is again NEG, as we said. So we have consciously put effort such that the Nokia Packet Core is cloud native at its basic foundation. So even when we started off with VNFs, we embraced cloud native principles. And now with containerized network functions, we have implemented a decomposed microservices architecture. The state is decoupled from processing to allow scale out and failover of pods that implement the network function. The containerized network functions fully leverage Kubernetes integration and are completely agnostic to the underlying infrastructure and the CAS and PaaS layer that they run on. So essentially, same instance of packet core CNF can run on any cloud that is enabled by different platforms, as I show here at the bottom. And that includes hyperscalers platforms as well, AWS and Google. And this is without any fundamental change to the application workload itself. All we do is expect baseline requirements to be met by the infrastructure such that then the workloads can run on any of these platforms. And Nokia NEG Core CNFs have been certified and tested on VMware's NFVI and the Tanzu Kubernetes platform that Ninad is going to talk about later, bringing a pre-integrated and tested solution for the operators to the market. And of course, the integration also includes full lifecycle management and DevOps automation. So, automated code pipelines, software upgrades, canary testing, and such. Okay. So then let's also, besides the NEG core, look at the user plane function, which given these high bandwidth, low latency services is at the heart of packet core, right? So a high performance UPF that is NEG is key for delivering services that have varied requirements, as we just saw, whether it's massive session density or high bandwidth and low latency. And with high bandwidth services such as eMBB or fixed wireless access, the UPF footprint becomes especially critical to optimize because it has a direct impact on the total cost of ownership. So therefore, the goal of a high performance user plane is to provide the highest throughput and lowest latency in a minimal footprint. That's where you would see the cost advantage. So lower cost, lowest cost per bit, high throughput, low latency. And such performance optimizations requires, of course, support from the application workload that implements the data path processing for a 3GPP UPF pipeline. But it also expects the underlying virtualization platform infrastructure to provide certain capabilities. And when I talked about 3GPP UPF pipeline that is implemented by the data plane architecture, this includes processing the packet, doing tunnel encapsulation, decapsulation, doing flow classification, counting packets for charging, applying rate limiting for session AMBR, mirroring traffic for lawful intercept, so whole 9 yards. And in addition, this user plane processing can also include application-aware services and charging that requires deep packet inspection, and then stateful network functions such as NAT and firewall. So it's a fairly involved beast that the UPF is. So it does need both the right architecture at the application level, but also platform tuning and support from the underlying platform. The right data plane architecture that can efficiently utilize the multi-core CPUs available today to implement the UPF pipeline, coupled with the platform tuning that provides efficient I/O and guaranteed resources for the user plane function is essentially key here. So let's just double click on both these aspects, both the data plane architecture, design tenets, as well as the platform tuning. Yeah, let's move the slide, Ninad. So if you just decompose a UPF, look a bit deeper, the most performance impacting part in packet processing is the I/O operation to get the packet in and out. Therefore, minimizing number of I/O loops as the packets are processed through the UPF pipeline and the stateful application-aware services on the SGI LAN or N6 interface will result in high performance. So Nokia provides a very streamlined architecture where the stateful DPI-enabled services and NAT and firewall can be integrated within the UPF itself. So this eliminates, multiple VNF or CNF or appliances providing these services. It essentially also minimizes the east-west traffic in the data center. So packets enter into the UPF once, is subjected to basic UPF pipeline that I described before, as well as these stateful services, and exits out of the UPF. That is, it is a single I/O pass and cracking of the packet. So what this does is really minimize the latency, it minimizes the overall footprint, and reduces the number of network functions that an operator will need to manage. So this is the streamlined architecture. Of course, based on your preference and your situation, we also allow separate service functions external to the UPF and efficiently steer traffic through them. But we do have the option of streamlining these within the UPF. So this is one key option that we provide for our customers that give us the performance and low latency. Let's go with the next slide. You can play it out, Ninad. So another key innovation on Nokia UPF is to use all the core CPU cores in a multi-core system for processing a single flow. And this becomes really important in certain applications. I'll go through that. But the alternative approach is of pinning a single flow to a single core in a multi-core system, as is done by some vendors. But this approach has significant pitfalls in our opinion. So for instance, if all cores are utilized enough, a new flow that is pinned to that core may drop packets and experience degraded SLA for the user. So this also can result in uneven loading on the cores, making any kind of capacity planning unpredictable. Also, we notice that processor technology as it evolves is moving more towards high core density rather than faster cores, right? So the issues with load distribution based on flow hashing is not solved with the newer CPU families. And these bottlenecks become especially visible when you look at speed test, which of course with carriers is a day one application to begin with. And also as you move towards longer lived high def video flows, this notion of pinning a flow to a single core is not the best idea. So in the Nokia UPF, we utilize all the cores by distributing packets of a flow amongst multiple cores and then doing sequencing of those packets. So this gives you a very balanced utilization, very predictable SLAs overall. So it's a much, much better approach. And we'll show you some results for a high throughput fat flow forwarding with a Nokia UPF on a VMware platform. Okay, we can move over. So another key requirement with UPF that we see is flexibility and independence in scaling and placement in order to address different services or service slices. For instance, for edge computing applications that are extremely latency sensitive, UPF of suitable scale, maybe very small UPF, or if you're talking about, high bandwidth, then the UPF may be larger, but the UPF would need to be very distributed to the edge, far edge locations closest to the user, while the control plane may be centralized in a regional data center. So that decoupling of control and user plane via 3GPP construct called CUPS, control and user plane separation, is really important. And you may, see that for a centralized EMBB type service, you may build a big UPF that can horizontally scale out and is centrally placed. So really these different services place different requirements on UPF, and CUPS in a way enables these service slices with different variants of the UPF. But one other thing, in order to fully realize the benefits of service-specific UPF variants that are enabled with this CUPS architecture, what you need is also automated deployment, scaling, and lifecycle management of infrastructure layer, the CAS layer, and also the different flavor of UPF workloads as well. But essentially what we're trying to say here, CUPS is an enabler of giving you these different user plane slices based on the services you're enabling. And this is something which we have built not just with 5G, but with 4G as well, and have deployed it at scale. Let's move, Ninad. And then very quickly, I mentioned before, a high performance UPF is a function not only of the right data plane architecture that we briefly touched on, but it's also a function of what the underlying platform can do. For a high performance user plane function, of course, choosing compute with high core density and large layer 3 caches and NICs with the right capabilities, for example, supporting SRIOV pass-through, is essentially a prerequisite, right? But beyond that, you also need tuning in the infrastructure and the cache layer to support high throughput, low latency, and deterministic performance that you need to minimize overhead and provide guaranteed capacity, right? So examples of minimizing the overhead in packet processing, the settings that you need at the platform, at the infrastructure and cache level are, enabling SRIOV, acceleration with DPDK, supporting huge pages so you don't do page swaps as often and lookups as often, so faster references to memory. Also, in a multi-socket systems, having NUMA alignment with respect to CPU, memory, and the NIC. And then, besides minimizing overhead with these techniques, also guaranteeing capacity and scheduling for high-performance UPF because you want predictable performance. We require things like CPU pinning and isolation, both at the worker node or the VM level, as well as the container level, right? And then another example is having dedicated pool of these worker nodes or servers running these pods because they have different characteristics, as I just outlined, with respect to acceleration and the other settings. So these are the baseline capabilities needed from any platform that needs to host a high-performance UPF. And Ninad will provide more light on how VMware Telco Cloud Platform provides these capabilities. So over to you, Ninad.
Thank you, Sanjay. That was a great overview of Nokia's 5G core, in fact, any G core and UPF architecture. And thank you for going into the details of the architecture and that is something which we from the platform side appreciate and would like to understand more as we work jointly and bring out consistent solutions for our customers. Now that we have heard the Nokia packet core architecture details from Sanjay, let's go next into VMware's solution, the platform on which this particular application is sitting for this particular test and session which we created. VMware's vision, as we know, is to support any device on any application, any core, on any cloud. In this particular case, we're talking about Telco Cloud and the applications such as the Nokia's NEG core UPF kind of applications. Now, to support this vision, VMware has released Telco Cloud Platform. This is a consistent platform which is meant to accelerate the move to 5G, help service providers and NEPs and NF vendors such as Nokia accelerate the move to the next generation 5G. The Telco Cloud Platform, short TCP, has built on 4 tenets. First tenet is to have a common platform for both VNFs and CNFs. Similar to Nokia's philosophy of having NEG supporting multiple versions, multiple generations, we believe that service provider customers are going through this transition from 4G to 5G. And the platform which we have out there, TCP platform, the key part is it's a common platform for both 4G and 5G kind of deployments. It helps with the transition from 4G into 5G while keeping the investment protection which service providers go ahead with VMware. The second tenet is multi-cloud, where the key goal is that while customers choose VMware, we want to give them the flexibility of deploying this TCP platform on any cloud of choice, be it on-premises or be it VMware on AWS, VMware on Azure, VMware on Google, etc. Name your cloud. Through TCP, we are giving a consistent platform for customers to deploy a Telco Cloud Platform across on-prem or on multi-cloud architectures, giving the flexibility of VMware Anywhere and the flexibility for service providers not to be locked in to one particular cloud provider. Third is automation. If you look at the scale and the complexity, which we just saw, it is very important to give a simplified way to automate and deploy these kind of applications. And that's where Telco Cloud Platform comes in with its automation layer. The tenant is to focus on simplified automation from core, edge, RAN, and public cloud. Same automation layer, same operation layer, end to end. And finally, it's the certification, the engagement with our NEPS partners such as Nokia, where we work closely and certify the network functions on Telco Cloud Platform and certify them so that service providers have a peace of mind that the vendors have worked together, verify the application, and come to them for a complete solution. With that in mind, let's go into more detail of the Telco Cloud Platform. Telco Cloud Platform, if you look at the stack, let's start from the below. It's based on Telco Cloud infrastructure, which is essentially the key vSphere, NSX, ESX, vSAN based layer, the layer of virtualization that we all know and love and have multiple kinds of applications deployed on. On top of that is Tanzu for Telco. Now, Tanzu is VMware's Kubernetes distribution, hardened by VMware and supported by VMware. Tanzu for Telco is a telco-specific edition of Kubernetes, Tanzu. And the reason for that is we believe there's a set of features that we saw which are needed to support NFs, telco NFs, things like SRIOV, CPU pinning, huge pages, etc., and node customization. And that's where Tanzu for Telco is a specific offering for telco-specific use cases. On top of that is the automation layer, Telco Cloud Automation, TCA for short. And that is a purpose-built product by VMware for automation and orchestration of network functions. And finally, day two operations for this network functions and for the network service is very important. And that's where VMware has, again, a purpose-built product called Telco Cloud Operations, which layers on top of the infrastructure and the automation layer and gives dashboards, NOC services, metrics, etc., so that the operations of your platform is seamless. By the way, key to note is that this platform which we see over here, these 4 layers, is consistent across core, edge, RAN, and cloud. You can have the same platform anywhere in your network. Of course, in some cases, in case of RAN, it's a more thin footprint as compared to core, but the premises is consistent. The operations is consistent. The automation, the orchestration, everything is consistent end to end. And by the way, as we look at multi-cloud or hyperscalers, again, the same thing, consistent platform as you bring your NFs to AWS on VMware or VMware on Google, Azure, etc. Let's now dig a bit deeper into the Telco Cloud Platform architecture. At the bottom of the slide, you see the key virtualization elements which make up the virtualization layer, which is vSphere, vSAN, NSX, and the vRealize suite. Now, in case of 4G, in case of VNFs, there is typically a Vim layer which manages the VNFs network functions, and that's where you see vCloud Director or VIO. A lot of our customers use vCloud Director or VIO. VIO is VMware's open stack-based solution for managing the NF and acting as a Vim layer on top of the infrastructure layer. In case of 5G, as we go into or in case of modern applications like Nokia's UPF and mobile core, we see that containerization is coming more and more into play. That's where VMware's Tanzu for Telco would be is a layer on top of our core infrastructure, and where CNFs would run and operate. On the top of the slide, you see the Telco Cloud Automation, which basically stitches all of these things together. It has two key functions. One is the automation of the infrastructure. So infrastructure automation, bring up, deployment, container, CAS, customization, deployment, upgrade, management, etc. Making sure that the container stack or Kubernetes stack is aligned to the requirements of the NF. And then the second function is network function management. So NF management bring up automation of the NF itself, in this particular case, Nokia, and the service management on top of it. This full stack gives a complete operational view and all the operational elements needed for a service provider to run their NFs. Now, let's go a bit more deeper into the Telco Cloud Automation layer, the top layer of this stack, right? So as you can see in the bottom of the stack, Telco Cloud Platform across the board, from core, edge, RAN, near edge, far edge, throughout, right? Having a consistent platform. Again, that's very important when it comes to operational costs and operationalizing your distributed, disaggregated 5G architecture. If you look at the Telco Cloud Automation on top, you'll see key elements. First is closed loop scalability. How would a platform react when an NF needs to scale up, scale down? Say you have an influx of users, influx of traffic. The NF has to scale up, the UPF has to scale up, scale down. How would the infrastructure know to react to it? That's where Telco Cloud Automation comes into play. It connects back to the infrastructure, scales up, scales down the resources, the networking configuration, etc., to make sure the closed loop scalability of the NF. The second part is self-healing, right? So as part of NFs, there's a need for self-healing. And that's where you see a need for making sure that the full NF can self-heal, and the automation layer can talk back to the infrastructure for self-healing. The third part is customization, right? So the detailed architecture which you saw from Sanjay about the kind of node configuration needed, SRIOE configuration needed, the CPU pinning, the details which are needed, can be templatized. Telco Cloud Automation can create a template out of it. Make sure then when you deploy the template on any location throughout the network, it is automated, deployed, and the customization is automated across the board. This is especially important when you're doing scaled deployments. Think of hundreds, thousands of nodes and so forth, going to each site, managing configuration and managing node customization is a huge pain from an operational cost, rather, from an operations perspective. TCA automates that so that just one place you put the template, and throughout the full stack, you have this automation done. And finally, CI/CD, which is a very important tenet for containerized NFs, right? So in the containerized NFs, there's a continuous integration, continuous development aspect. And for that, the system has to be able to absorb new iterations of the NF and be able to give a way by which those NF can be presented to the service provider. Through our pipeline, we essentially ingest CSAR files into sort of a catalog factory. And there's an automated way to deploy a test environment, run tests on this new CSAR, or this updated CSAR of the NF, and then bring it back into the main repository, creating a complete closed loop of a CI/CD pipeline. By the way, all of this, as I mentioned, is via a centralized or a common onboarding platform. So you don't have to go to each location to do this. From a single pane of glass, you manage this end to end. Specifically on the data pane performance perspective, right? So we talked a lot about the automation, the orchestration, the ease of use, the customization. which is great. But then when it comes to actually the guts of the performance of the key applications like the UPF, we have done a lot of work to make sure that the platform is deterministic when it comes to performance. Deterministic at high packet rate, support very low packet loss, if any, and make it easy for customers to evolve into this 5G architecture while maintaining the performance which they need for their services. We also support multi-tenant networking and routing to support various kind of configurations. And self-tuning, which you talked about, self-healing, self-tuning, and optimized way to position, place, and pack the NFs in a infrastructure such that the performance of the NFs are optimized. At scale, you see a need, as I mentioned, of managing deployments in 100,000, 50,000 sort of scale deployments, especially when you go to RAN, private edge, or even large scale core deployments, right? And that's where this comes into play, where you see that configurations such as node pool, and again, these are some of the things which are mentioned by Sanjay, which Nokia as an application needs from an application, from a platform. Now, you might have various kinds of infrastructure throughout your architecture, right? But how do we map the NF's needs with the infrastructure which you have? And that's where the platform comes into play. You can create a template which presets the node configuration, the node customization, the latency requirements, predefine your configurations like what you need from SRIOV, DPDK. The system understands the need for resource optimization, placement of resources. In some cases, you need to pin CPUs for the performance which you need, right? And the NUMA alignment on a multi-socket architecture, right? With Telco Cloud Automation and Telco Cloud Platform, you create templates and which align with the NFs and simply deploy it at scale across the board. This gives a simplified way of managing the full end-to-end platform. So that's all about Telco Cloud Platform and the innovation which we have brought to market to optimize VMware stack for telco applications, such as Nokia's application UPFM Mobile Core. Next, I'm going to hand it off to Sanjay to talk about the performance, rather the testing which you have done jointly, and the results and the performance results which you have seen from that testing. Sanjay, off to you.
Yeah, thanks, Nishant. Can you move to the next slide, please? Okay, so having gone through some of the key considerations for performance, optimized UPF, including requirements for the underlying platform, what we show here is a summary of throughput benchmarking that we did with Nokia UPF on VMware TCP platform that Ninath talked about. So here the UPF is performing the full 3GPP user plane pipeline that we had described before, and it's running as a CNF on VMware Tanzu Kubernetes grid. The compute that we have used in this testing is HP DL385 Gen 10 plus 8 Gen 10 plus servers, which have AMD EPYC 7713 64 core sockets, and we're using NVIDIA ConnectX-6 NICs. The traffic generator here is simulating the RAN and the content/internet part. So with this setup, we have observed over 360 gigabit per second of throughput at average 950 byte packet size with roughly 80% CPU utilization. So it's a pretty high performance UPF that we see on the platform with all the tuning that we mentioned and the architecture that we have in place for the UPF. Can we move to the next slide, Ninath? In addition, the innovation that we discussed in terms of utilizing multi-core platform well in order to achieve high single flow throughput, which is again important in speed tests and large long-lived video flows, we also show that here. So this is a single flow single fat flow, where the system is already on the right side is what you see with our system here, with our UPF. The cores are already utilized evenly, and no single core could have handled this single flow, the new flow that is coming in. But because of the fact that we distribute the flow across all available cores, you see this kind of throughput that we are able to achieve with a single flow. And again, here the testing was mainly gated by the traffic generator. So the architecture still allows you to go higher. So both a high throughput, low latency optimized user plane, as well as high per flow throughput. And just looking at the numbers we saw, the 360 gig is basically on this single server. As a UPF instance, we can scale out, meaning we can add more compute to achieve a terabit plus on this platform as well. But what we are here showing you is numbers with a single server instance. But again, you can scale out to get even higher performance. And on the flip side, for a far edge location, we can scale down the UPF to what we call a micro UPF, down to 3 physical cores, giving you between 5 gig to 10 gig of throughput in just 3 physical cores. So the flexibility for the UPF is another thing that we are able to show. So with that, we conclude the presentation. Hope it gave you a good preview of what we are jointly bringing to the market to evolve your current core to offer 5G standalone access seamlessly without compromising performance and in an optimized footprint. So I think we conclude here. We'll be happy to take any questions offline or interact with you offline. Both Ninad and I'll be available. So over to you, Ninad.
Thank you very much, Sanjay, and thank you all.